11 people died and 5 million barrels of oil spilled into the Gulf of Mexico because of the Deepwater Horizon explosion. While often described as a sudden accident, the disaster began hours before the first spark, hidden inside routine operations. To understand why, we are walking backward through the Chemical Safety Board's timeline, hour by hour. This forensic look reveals how a specific chain of human decisions systematically dismantled the safety systems designed to prevent a blowout. The setting is the Macondo well, located under 5,000 feet of water. The crew was finishing temporary abandonment, a process of plugging the well so the rig could move to a new location, while leaving the site secure for future production. Temporary abandonment is a high-risk transition. As the crew removes the heavy drilling mud that weighs down the reservoir, they rely entirely on bottom hole barriers to hold back immense geological pressure. The blowout was the inevitable physical reaction to an organization systematically dismantling its own protective barriers. The timeline starts at T-11 hours. BP canceled a $118,000 cement bond log test to save time and money. That test was the primary way to verify the integrity of the cement at the bottom of the well, and without it, the crew had no way to confirm the barrier was solid. At T-7 hours, the crew pumped 454 barrels of heavy, leftover chemical material into the well to act as a spacer fluid. BP chose to use this unusual mixture primarily to avoid the cost of hazardous waste disposal on shore. At T-5 hours, the crew ran the first negative pressure test. This test checks for leaks by monitoring for pressure buildup. The drill pipe pressure should have stayed at 0, but it spiked to 1,400 psi. This was a clear sign that oil and gas were breaching the cement. Instead of stopping, the crew ran a second test at T-4 hours, this time on the kill line. While the kill line read 0, the drill pipe remained at 1,400 psi. Without formal procedures to interpret these results, the crew dismissed the anomaly as a harmless bladder effect. This is a classic example of the normalization of deviance, where dangerous data is rationalized away because it interferes with the schedule. 3 critical decisions have now passed, each with escalating warning signs. This pattern of ignoring data in favor of a predetermined outcome is common in high-hazard industrial failures. When an organization prioritizes a schedule over data, cognitive bias convinces highly experienced professionals that a failing well is secure. At T-2 hours, the crew declared the test a success and began replacing heavy drilling mud with lighter seawater. This action permanently underbalanced the well, leaving the reservoir pressure higher than the pressure inside the pipe. During the final hour, the crew missed multiple kicks, sudden increases in pressure and fluid flow. Poor alarm management and lost situational awareness meant the gas continued to rise toward the rig undetected. At T-0, hydrocarbons bypassed the failed cement, raced a mile up the riser, and erupted as a geyser onto the rig floor. The crew made a final attempt to survive by activating the blowout preventer. This 360-ton device is the ultimate mechanical barrier, designed to cut the pipe and seal the well in an emergency. The blowout preventer failed because it was activated too late. The massive pressure differential from the escaping oil and gas triggered a phenomenon called effective compression. As shown in this investigation diagram, the immense pressure physically buckled the drill pipe off-center. Because the pipe was warped and pressed against the side of the wellbore, the blind shear rams could not cleanly cut through it to seal the well. Emergency mechanical safety systems fail when they are relied upon to solve failures in situational awareness and early detection. The gas ignited, triggering explosions that consumed the rig and killed 11 workers. The Deepwater Horizon burned for 2 days before sinking into the Gulf. The resulting spill caused massive, long-term environmental devastation, contaminating the Gulf Coast ecosystem with millions of barrels of crude oil. This disaster was a catastrophic failure of management. To prevent similar events, regulators now enforce frameworks like SEMS, the Safety and Environmental Management System, which requires operators to manage the risks of the entire drilling process, not just worker safety. The operational takeaways are clear. Trust data over the production schedule. Never rely on a single physical barrier. And ensure emergency systems undergo rigorous integrity audits. If you want to learn more about workplace safety and OSHA rules, subscribe to HSE Study.